Good evening, and welcome to the Scientific Adventures of Beardman. Today we're beginning a unit on electricity. Today we'll be looking in particular at static electricity. Okay, so static electricity is, like when you take your socks out of the dryer and they're stuck to your silk shirt and you peel them apart. If you put them close together again, they seem to attract and stick to each other. Or if you take two of the socks, they'll tend to push away from each other. Well, static electricity comes from stuff going on inside the atom. So let's take a look really quickly at the structure of the atom. Okay, here we see a common picture of the atom. There's the nucleus here in the center with the electrons whizzing around the outside. Of course, they don't exactly whiz in circles like this, but we'll let that go for now. The basic idea that we need to get a hold of today is which particles have what charges and where they are within the atom. So the two particles that we care about that have charge are the electrons and the protons. Electrons would be defined as negatively charged particles that exist around the nucleus of the atom. We see this area that we call the electron cloud. And a proton would be defined as a positive charge that's in the nucleus of the atom. Okay? They have different masses, but once again, that's for another day. So the most important thing here is that the protons are stuck in this nucleus. They can't leave. They can't just decide to go somewhere else. They're stuck in the nucleus. The electrons, however, are out here around the nucleus. They are near the outside, and we'll learn that they're able to leave the atom. Well, they don't just happen to leave, but if something were to happen, they were to get enough energy, they could leave. The amount of energy it would require to take a proton out of the nucleus is extremely formidable. Okay, and so we're not likely to see that happen. Instead, the electrons are the things that will leave an atom. So if we are going to end up with an object like a sock that has a charge on it, well, what has to have happened is that the electrons have moved from one atom to another. You see, because normally an atom has the same number of protons and electrons. Well, it could be a molecule is the same number, but in a small area, normally the number of positive and negative charges are balanced out. So if we look at oxygen, say, typically you would say oxygen has 8 protons, and therefore it has 8 electrons. And that's what we'd consider a neutral atom. Now, of course, it may be sharing some of those, or it may have given some to the atom next to it, but within that very small area, the charge is balanced. Well, if something were to happen so it's not balanced, then we get an ion. Okay, an ion of oxygen maybe, say, took 2 electrons from another atom, and so now it's got 8 protons and 10 electrons. We could say it has a -2 charge because it has 2 excess electrons. Okay, or if we took something like sodium. Sodium has 11 protons, and it might give away an electron, or an electron might be taken away from it. And so if that electron is taken away, well, then we have a net charge of +1 because we have 11 positive protons, and now there's only 10 negative electrons because one of them was taken away. And so those are ions. That's how we get a microscopic object with a charge. Okay? Now the same thing can happen with the sock. The sock can get excess electrons that came off of some atoms somewhere, maybe in a silk shirt, that were happy to give away, or happier to give away, the electrons. And so the sock ends up with a negative charge because it has an excess of electrons. Now, the amount of charge that one electron has is very small for the kinds of things we deal with. If the sock had 1 extra electron, you would never notice that. Okay? So instead we have a larger unit that we use called a Coulomb. Okay? A Coulomb is essentially the amount of charge on 6.241 times 10 to the 18th electrons. Okay? So now we have a conversion factor. If we know how many excess electrons something has, we can set up a conversion factor with 1 Coulomb over 6.241 times 10 to the 18th electrons. Okay. You often see that number flipped around, though, by simply saying, how much charge is there on 1 electron? Well, 1 electron has 1.602 times 10 to the negative 19th coulombs of charge. And so you could use that as your conversion factor as well. Either one will give you the same answer, because either you've got 10 to the 19th in the numerator or 10 to the 18th in the denominator with the appropriate number out front. And so whether you're multiplying by a small number or dividing by a large number, you end up with the same answer. So those two numbers are kind of well-known numbers. That's why I mentioned both of them. Now, as we start to look at what effects these charges have, which we actually did at the beginning of the video, we saw that these charges can make your silk shirt and your cotton socks stick together, or they can make two cotton socks kind of push each other apart. The question is why? Well, it turns out we don't know. We don't really know why this electron knows that this electron is over here. So we had to develop a model to understand or to explain or to help us identify when there would be forces. And that model we came up with is called electric fields. Okay? Electric fields basically describe why one charge knows that another charge is there. Okay? So here's our definition of electric fields. A field in a region of space that exerts electric forces on charged particles, or a field produced by electric charges, or by changing magnetic fields. Okay, you can see the definition is broken into two parts. You can see it's got one part that defines what the field does, that it puts forces on charged particles, and the second part that describes how it was produced. It was produced by electric charges. Okay. For now, we're going to just ignore kind of the portion that says, or by changing magnetic fields, because I haven't taught what magnetic fields are yet. So when we get to that, we'll kind of revisit this and see how changing magnetic fields can produce electric fields, which really gives you light. Pretty exciting, huh? So when we have a charge, okay, like let's just say we have a positive charge, okay, that positive charge will have, if we draw the electric field, we'll have a bunch of arrows around it, okay? And those arrows will point away from a positive charge. Notice that the electric field is getting weaker as you get farther from the charge. Just like gravity gets weaker, the gravitational field gets weaker the farther you get from a planet, same thing. As we get farther from this positive charge, the field will get weaker, but it's still always pointing away from that positive charge. A negative charge, on the other hand, has all the electric field arrows pointing towards it. Okay, so the electric field is pointing towards a negative charge. Okay, now one way of defining the electric field is that the electric field is the amount of force that would be put on a 1 Coulomb object if it were placed at that location in space. Okay, so if we take a 1 Coulomb object and we put it here, then we say how much force would that experience, and that is what we call the electric field. Okay, so now notice that if we put a positive charge next to this positive charge that's creating this electric field, well then it's going to follow the arrows, because those are the direction the direction a positive charge will be pushed, and it will get pushed away. In other words, a positive and a positive repel. To talk about what happens when a positive charge is put next to this negative charge, I've got a friend to teach you about that. Hit it, Paula.
But when we get together, it just all works out.
She's Did you hear that? Opposites attract. Teach it, Paula. That's right. That's right. Opposite charges attract. I bet you never knew that Paula Abdul was a physicist. Well, guess so. I don't know her personally, actually, but she is clearly, trying to teach the world opposite charges attract. Because as you can see, if we've got this negative charge here, all the electric field arrows are pointed towards it. And if we take a positive charge, opposite of that negative charge, and put it in that electric field, it's going to be pushed the direction the electric field is pointing, and they will attract. Yes, opposite charges attract. Thank you, Paula Abdul, and that's going to wrap it up here for electrostatic charges on the Scientific Adventures of Beardman. Have a good day. Enjoy your 1980s music.